Hey y'all, so in Unit 7 we are going to be looking at logarithmic functions. Today we're just going to introduce them. I'll kind of go over what a logarithmic function is, where does it come from, that sort of thing. And we'll also look at how to evaluate logarithmic functions. And towards the end of the lesson today, we'll look at how we can start to use our understanding of logarithmic functions to solve certain types of equations, because it can be pretty useful in some cases. So before we actually get into this idea of a logarithmic function, I want to take you back to Algebra 2, maybe a little bit in Algebra 1, and talk about another type of function, which is called an exponential function. This is something you're probably a little bit more familiar with. So an exponential function, as you may recall, is going to be any function where your unknown is your exponent. So the most basic type of exponential function is going to look like this: y equals b to the x, where b is your base. This could be any number. It could be like 2 to the x, 3 to the x, whatever. So this is how most of those equations are going to be formatted. Just to remind you what the graph of an exponential function looks like. In general, if we're going to assume that this number is bigger than 1, so like 2 or 3 or 4, something like that, the graph will typically look like this, where your y-intercept is at 0, 1, okay, and then you have this other point, 1, whatever the base is. Okay, so this point would be 1, the base. This point right here, 1, 0, 1 rather. And you can graph any other function that's kind of set up like this just using those two coordinates. There may be occasions where you have transformations on that, but the transformations are going to work exactly the same as they would for the sinusoidal functions and also for just any other functions that you've dealt with transformations in the past. So like, for instance, let's say you had a coefficient on this function. So you would want to multiply some number by 2 to the x. So maybe you have something like 3 times 2 to the x or something like that. So this number is going to cause a dilation, a vertical dilation, and the way that that will affect your graph is basically you'll just multiply all the y values by this number. So like, let's say that was a 3, then instead of this being 0, 1, it'd be 0, 3. This would be 1, 3 times whatever the base is. And so you'll still have the same horizontal asymptote that you would normally have, but the graph is going to sort of increase a little bit faster there. If you have a negative number in front of that, or let's say you just have like negative b to the x, that's going to cause a reflection across the x-axis. So y equals negative b to the x is going to look something like that. If you have something like y equals b to the negative x, instead of reflecting across the x-axis, you're going to be reflecting across the y-axis. So this is getting a little messy here, but this y equals b to the negative x would look something like this. So basically it's just a reflection over the y-axis. So these are just some basic transformations. As you know, there are some other ones too, like you could add some number to the end of here to shift it up, subtract it to move it down. You could either add or subtract something to x, which would cause a horizontal shift left or right. So there's some other transformations you can do with that too. We're not really going to focus too much on the graphing piece of it. I just wanted to remind you kind of what it looked like, and it's going to help us hopefully kind of understand what a logarithmic function is a little better. So we're almost there. I know I said in the beginning we'd be talking about logarithmic functions, and so far I've just been talking about this old exponential function. But we will get to it. Just hang in there. So this is what an exponential function is all about. Another topic that we've talked about in the past, and you probably have talked about in Algebra 2, is what an inverse function is. So an inverse function is when you take a function and literally invert it. You take your inputs and they become your outputs and vice versa. In Algebra 2, you probably learned how to actually find an inverse function. Let's say we had a real simple equation like 2x plus 3, and we want to find the inverse. In other words, we want to find a function so that the domain and range are completely reversed, so that all the inputs become outputs and vice versa. To do that, you rewrite this as y equals 2x plus 3. You would swap x and y, because that's really what we want to do here, is change what is the input and what is the output. Then you would solve for y by subtracting 3, dividing by 2, and you get this equation. This equation is going to represent the inverse of the original one, right? So the inverse of 2x plus 3 would be written like this. You'd say f, put a little -1 up here, and you'd read this as the inverse of f of x is x minus 3 over 2. So these would be inverses. We saw earlier in the year what some of the inverse trig functions looked like, and we saw that sometimes you have to restrict the domain of the function in order to get an inverse that is also a function. But one of the things that I want to emphasize here when we're talking about inverse functions is their representations graphically. So like, for instance, let's go back to that sine of x that we looked at in the last semester. Let's say we have f of x equals sine x. We know that basically that's going to look like this, right? Roughly. But in order to talk about the inverse of this, we had to restrict so that we had to restrict the domain of this so that we wouldn't have any domain problems, and so that our inverse would also be a function. So we really only looked at sine to in between negative pi over 2 and pi over 2. So it was really just this segment that we wanted to invert. This little piece of a curve here. And when we inverted it, we saw that it would look something like this. So this point, which was at negative pi over 2 comma negative 1, now be at negative 1 comma negative pi over 2. So it would look, well, okay, so this is going to be a little tricky to graph here. But, well, here, let me actually pull this up separately. So you can see as we graph sine x, you get this periodic function that goes on forever from negative infinity to positive infinity. But if I were to invert that completely, you'd get a curve that kind of goes up and down like this. That would not be a function. So in order for the inverse to be a function, we do need to restrict that domain so that when I invert it and get something like this, now you can see that curve, which wants to do this, now can be a function. There's no input that has multiple outputs. So anyway, the point I'm trying to make here, though, is that when you look at this graph closely, you'll see that they are reflections over the curve y equals x. And this is going to be true for all inverse functions. So if I talk about y equals 2x plus 3, like that original linear function that I was referring to above on the notes, and its inverse, which is x minus 3 all divided by 2, those are also reflections of each other over y equals x. So that property regarding the graphs is going to be true for all inverse functions. And at this point, you're probably wondering, okay, well, what does this have to do with logarithmic functions? And I promise you we're getting there. So let's get back to the exponential function. Let's kind of merge these two ideas, this exponential function, the inverse function. So let's say we had a function like y equals, let's see, 2 to the x. So real simple exponential function, right? So if I want to go ahead and graph that, it will look something like this. Real simple. I'm not gonna, I don't have any graph paper here, so it's not gonna be super accurate, but just the general idea is you've got this horizontal asymptote at y equals 0. You've got a coordinate at 0, 1, and then you've got a point at 1, the base, which in this case is 2. And you've got, here's your curve. It looks something like this. So that's y equals 2 to the x. And what I want you to think about is, what would the inverse of this look like? So like if this is f of x, what is the inverse of f? Let me do that in a different color here just to make it a little bit more obvious. What is the inverse of f here? And so without actually trying to solve for it algebraically, because we don't have those tools yet, let's look and see what it would look like graphically, just to sort of get a feel for it. Instead of there being an asymptote at y equals 0, since the domain and range are flipped for the inverse, that particular one would have an asymptote at x equals 0. It would be a vertical line that this function wouldn't cross. You've also got this coordinate at 0, 1 for the exponential function. So for its inverse, you'd have a point at 1, 0. Instead of having a point at 1, the base, which is 2, you would have a point at the base, 1. And so your curve looks like this. Notice how this would be a reflection across the line y equals x, right? So this graph is the inverse of this function, and that inverse has a name. So here we go. Here's the big reveal, is that the inverse to an exponential function is a logarithmic function, okay? So a logarithmic function is the inverse of an exponential function. Now, since logarithms are defined using exponents, each logarithmic expression is going to have an exponential, an equivalent exponential form, and vice versa. I haven't really shown you how to properly write this yet, but I guess now's as good a time as any. Is the way to write this inverse of the exponential function, called a logarithmic function, looks like this. You just literally write the letters log for log, for logarithmic. We want to know what the base is. Okay, so the base here is 2. So where you write that is a little subscript right after the log, and then of x. So this is the inverse of this. Okay, these are inverse functions of each other. To put it simply, a logarithm is an exponent. Okay, so if you're ever asked to answer the question like, what is a logarithm? Well, the short answer, the simplest way to put it, is that a logarithm is just an exponent. And so when we try to evaluate logarithms, you want to be thinking about, okay, what's the exponent? So whenever you write these exponential and logarithmic expressions, or equations, you can sort of rewrite them using the other way. So let me show you a couple of examples of what I mean by that. So first, let's think about, let's say you had an equation like 4 squared equals 16. Okay, obviously this is true, right? We're not trying to like solve anything. I just want you to see that this can be rewritten using logarithms. Okay, so this equation is equivalent to the equation log, now the base is 4, of 16 is 2. Basically what the saying is 4 squared is 16. Remember that the logarithm is the exponent. So what the logarithm equals should be the exponent. The base is the base in both cases here. But what the logarithm is the exponent. So make sure your exponent is on this side of the equation. Similarly, let's say you had something like 3 cubed equals 27 is equivalent to, I got a full expression here, is equivalent to log, now let's see here, the base here is 3, and you should have log base 3 of 27, forgot my parentheses up here, equals, well, what is the logarithm? The logarithm is the exponent, so here it'd be 3. So whether you write it like this or write this like this, you're saying the exact same thing. It's just a matter of what's more useful to you in terms of what are you doing. You can also go backwards. You can write a logarithmic equation as an exponent. So if I have something like log base 5 of 25 equals 2, I can rewrite that as 5 squared equals 25. Sometimes it's a little easier to go this way, I think, because you're so much more used to seeing exponents. So like if once you write the equation, you can kind of check it. Like if you mess up putting the numbers in the wrong places and you write something like 2 to the 5th is 25, that should sort of raise a red flag. Like this equation should be correct. Otherwise, this wasn't an equation to begin with. So yeah, you can go both ways. We'll just do one little quick last example here. If I have log base, let's say log base 2 of 8 equals 3, you're saying 2 to the 3rd power is 8. So to rewrite this, you would say 2 to the 3rd power is 8, which is also true. So we'll practice rewriting these for sure. But what I want to get into before we start doing a bunch of practice here is there are some two special logarithms. So logarithms that have a very particular base that we write in a slightly different way. So instead of writing like log, base, argument, exponent, they're just written a little bit differently. So let's dive into those. So we've got these two special logarithms. We've got one that's known as the common log and one that's known as the natural logarithm. The common log or the common logarithm is when the base is 10. So if you have log base 10 of x, you typically will not write that down, that 10. You'll typically just see log of x. So if you do not see a number written in the base is assumed to be 10. This is something that can be different in different textbooks. I've seen these two kind of reversed. So be careful when you're looking online. Sometimes there are some sources that will use this shorthand of just log x where the base is something else. But for our purposes, we're going to say if there's no base written here, then it's assumed to be 10. The natural log is another sort of special logarithm where the base is Euler's number. Okay, so this Euler's number is about 2.7 something, and it'll come into play a little later on, a little bit more. But this is another very special logarithm where it has its own notation here. If the base is Euler's number, which is written as just e, you write it as ln of x. Okay, the natural log of x is the way you read it. You can, like, these letters are kind of backwards because this notation was developed. It was a French person came up with this notation, and in French, they say their nouns before their adjectives, which I guess kind of makes sense to know what you're describing before you describe it. But in English, we say the natural log natural. Either which way, the correct notation here is going to be ln. So those are the two special logarithms. So like if I say, oh, go ahead and write, 10 to the x equals 200 in logarithmic form, you're not going to write log base 10 of 200 is x. You're going to say just log of 200 is x. Okay, you're not actually going to write the 10 here. Same thing here. Like, let's say you have, the natural log of x equals 5. Okay, well, let's rewrite this. The base here is assumed to be Euler's number. So you would say e to the power of 5 equals x. So you can kind of go both ways there. So in general, I've shown you a few examples here of kind of going in between exponential and logarithmic form. Let's just kind of summarize that. In general, we want to say if you've got y equals log base a of x, then that is equivalent to saying a, or you know what, let's not use a, let's use b for base. This is equivalent to saying b to the power of y equals x. Okay, so if you're ever trying to go back and forth, this is kind of, where everything goes. The base is the base in both cases. The logarithm equals the exponent. And as long as you can remember those two things, it shouldn't be too hard to remember like how to go in between. Okay, so that kind of summarizes kind of the basics of logarithms. What I want to do is go through some sort of rapid fire examples of how to evaluate logarithms. Now, I know you'll have a calculator, so this might be a little trivial, but I think in order to really understand what a logarithm is, I challenge you to try to do some of these without a calculator. So let's evaluate some logarithmic expressions here. So I'm gonna write some down here, and I'll just kind of talk through how I would think about evaluating them quickly. So when you're trying to evaluate log base b of x, you want to think b to what power equals x. Okay, so anytime that I ask you to, if I ask you to say, what is log base 3 of 9, the question you should really be asking yourself is 3 to what power is 9? In other words, 3 to what power is 9? Now this can make it a little bit easier, right? Like 3 to what power is 9? Well, that's pretty obvious. 2, right? So log base 3 of 9 is 2. So these can be pretty easy like that. Let me give you another easy one here. Log base 4 of 16. Well, that would also be 2 because 4 squared is 16, right? Just like up here, we had 3 squared was 9. Here we have 4 squared is 16. Now, if I give you a common log and I just say something like log of 10,000 here, so log of 10,000, the question would be like 10 to what power is 10,000? 10 to what power is 10,000? Well, let's see. That would be to the 1, 2, 3, 4th power. So that would equal 4. This can get a little trickier, not too bad. But if I said what's natural log of e to the 14th, you want to be asking yourself e to what power? Because remember, when you see natural log, the base is e, or Euler's number. So e to what power is, what's in the parentheses here? E to the 14th. So e to what power is e to the 14th? Well, when you write it out like this, it becomes a little more obvious, right? That number has just got to be 14. Let's do a few more. I want to do a bunch of these because I think the more you do this, the clearer it will become, how you handle problems like this. So let's say I have something like log base 3 of 1/3, and I want to know, okay, well, what does that equal? So we have the base, which is 3. 3 to what power is 1/3? Now this one might not be as obvious. Been a long time since you've talked about any kind of exponent properties or anything like that, but a to the negative 1st power is going to be 1 over a. So in this case, this is just a little exponent property that we'll revisit that next time. But 3 to what power is 1/3? 3 to the negative 1 power is 1/3. So when you have these fractions, you just got to be a little careful there. Make sure you're reading it correctly. If we have log base 4 of 1/16, what is that going to equal? Well, 4 to what power is 1/16? If it's not as obvious, you might try to write this as a power of 4, right? 16 is 4 squared. So 1 over 4 squared means that this would need to be -2. All right, because 4 squared is 16, so 4 to the negative second power would be 1 over 16. Now, if you ever have a 1 in your argument here, so let's say we have like log base 6 of 1, or it could be log of 1, or natural log of 1. Anytime 1 is in here, you want to say, okay, well, 6, or whatever the base is, to what power is 1? And that answer is going to be pretty much the same every time, right? 6 to what power is 1? Well, 6 to the 0th power is 1. So anytime you've got a 1 in here, this is going to equal 0. Yeah, so even if you have something like natural log of 1, same deal here. It's going to be 0, right? Because e to the 0th power is 1. We're kind of doing a lot of examples here, but I feel like this is going to be useful. Log base 3 of 3. Okay, 3 to what power is 3? Well, that one's pretty obvious. 3 to the first power is 3. Natural log of e. Okay, e to what power is e? Well, anything to the power of 1 is itself. So this would be 1. So like if these are the same, that's always going to equal 1. Let's get a little trickier here. Let's say we have log base 25 of 5. Now, if you're doing this really quickly, you might just say, oh, 2, because 5 squared is 25. But the question here is that the base here is actually 25. So the question is 25 to what power is 5? Say, oh, well, 5 is smaller than 25. How can that be a power? Well, you might think, hey, well, the square root of 25 is 5, right? So maybe there's something there. Anytime you're taking a square root, that's essentially equivalent to raising it to the 1/2 power. So 25 to the 1/2 power is 5. And so that's where we're going to get our answer from here. Log base 25 of 5 is 1/2. Being pretty inconsistent with the colors here, that's okay. So similarly, like let's say you had log base 49 of 7, a very similar problem here. If the question is 49 to what power is 7, well, since 7 squared is 49, 49 to the 1/2 power would must be 7. It can get a little trickier, but not much. Okay, so let me just give you a few more that are maybe just going to push you a little further, but won't be too bad. So along this same kind of thinking with fractions, let's say we had log base 8 of 2, to where the question is 8 to what power is 2? Well, if 2 cubed is 8, then 8 to the 1/3 would be 2. If I had something like log base, let's say 27 of 1/9, okay, now we're getting real tricky here. These are going to be a little bit more of the harder kind of problems. Are going to look like this. Let me swing this up around a little bit. There we go. So the question here would be 27 to what power is 1/9? Well, now it's getting a little trickier. Like, okay, well, I don't know. This is really going to push the limits of your memory on the exponent properties, and don't fret if you don't remember all of them. We'll go over them a little bit more next time. But just want to kind of push you a little bit. Okay, well, if this isn't super obvious, it might be a little bit more obvious to write these as powers with the same base. And what I mean by that is, okay, so 27 is actually 3 cubed to some power, okay, equals 9 is 3 squared, so 1/9 would be 3 to the negative second power. Now we're kind of getting somewhere here. So 3 times what is negative 2? 3 times what is negative 2? That means that what needs to be negative 2/3. This one's pretty tricky. I'm not gonna lie here. Okay, don't get too scared off by this one. But basically, this one's gonna be negative 2/3. Again, I know you can use a calculator for all these, but I really think it is worthwhile to, at least in the beginning, try to do these by hand to give yourself an opportunity to really understand what a logarithm is, beyond just saying, hey, it's an exponent, because that is what it is. But to really try to evaluate some of these is a little trickier. So let's just do a couple more here. I know we're kind of spending a lot of time on these examples, but okay, so 25 to what power is 125? Another kind of weird one here. 25 to what power is 125? That doesn't work out perfectly, right? Like 25 squared is 625, something like that. It's gonna be way bigger than 125. So we need a way to kind of get there. You can think about it kind of like we did this one over here. You say, okay, well, 25 is actually 5 squared. 5 squared to some power is going to be the same as 5 cubed is 125. So 2 times something is 3, right? 2 times something is 3. So that something's got to be 3/2. Again, these are we'll spend some more time on this kind of stuff next time. But yeah, so that's pretty much it. Let's just do one last example here, just to kind of finish this out. We'll do log base 3 of the 5th root of 9. Yikes. Okay, let's see if we can compute this. So log base 3 of the 5th root of 9. We want to know, remember the question here is 3 to what power is the 5th root of 9? Okay, so can we rewrite this at all? Well, 9 is 3 squared. And the 5th root is the same as raising it to the 1/5 power. So I guess we could write this as 3 to the power of 2/5. Because 3 squared is 9, and then the 5th root would be 3 to the 1/5. So that question mark then, well, now it's a little bit more obvious here, right? 3 to what power is 3 to the 2/5 power? So that unknown needs to be 2/5. So these last few I know are a little bit trickier, but generally the question you want to be asking yourself is b to what power equals x? All right, and that's how you're going to evaluate these things. That's going to be the majority of what we're talking about today. I'm going to have you practice a lot on this in your homework. There's one other quick thing I want to show you as a little preview for what's coming up. We are going to spend the next few class periods learning how to solve more complicated equations for x. So let me just show you some simple ones real quick. So rewriting the equations like we did in the beginning can be helpful for solving equations. Like let's say I have log base 2 of x equals 3, and I want to solve for x here. Well, I can do that by simply just rewriting the equation as an exponent. So I could rewrite this as 2 to the 3rd power is x, and now I'm basically done, right? Like all I had to do is just rewrite it using the inverse, and I've got my answer here. 2 cubed is 8, and I got x equals 8. So not a lot of solving here, just have to know how to correctly rearrange it, and then you're going to be good to go. If I have log base x of 25 equals 2, I can approach it very similarly and say, okay, well, x squared is 25. Now these numbers are sort of chosen to be a little easy to compute here. Something squared is 25. well, that something has got to be 5, right? Or I guess it could be -5, but these bases are not going to be negative. That's something I kind of left out here. This came up right now that I guess I didn't really think about. But if we go back to the very beginning here, when we're talking about exponential functions, one of the requirements in order for this to be an exponential function, which I sort of glossed over, was the fact that this has to be positive and not 1. So if you get a base which is negative, or you get a base that is 1, it's very likely that you're going to have something that's undefined. So this cannot be -5. Okay, you can't have a negative base on a logarithm. For the same reason, an exponential function can't have a negative base. Okay, so anyway, we get that answer. It should be good to go. And so that's how you can rearrange some of these equations. Okay, so that's pretty much it for today. I want you to practice some of the practice problems. We will have a quiz next class that I'm sure I've already talked to you about, and I'll see you then.